Hi guys, today I'm going to present a video on doubly reinforced beam. So please kindly subscribe to Civil Learn for more videos. Introduction. Generally, steel is provided in the concrete beams to resist the tension while the compression is taken by the concrete. Singly reinforced beam means the reinforcement is located in the tension zone only and which can resist a limiting moment of resistance that is equal to that of a balanced section. As we already seen in the previous videos, we are having three types of sections, that is balanced section, under reinforced and over reinforced. Balanced section means x nu is equal to x u max, that is called balanced section. If x nu is less than x u max, that is called under reinforced. If x nu is greater than x u max, that particular section is known as over reinforced. But in many cases, the size of the concrete beam has to be restricted due to its architectural appearances and practical requirements. For example, if we design the section for singly reinforced for a maximum moment, the section will be more size. So to reduce the size of the beam, we will go for doubly reinforced beam, but the same section is required to resist a moment that is greater than the balanced section. Based on these circumstances, additional moment of resistance is obtained by adding steel on both the tension and compression zones. Such as sections is known as doubly reinforced beam. So doubly reinforced beam means the reinforcement is located in both compression and tension zones. These are the properties of doubly reinforced beam section. So this is the doubly reinforced beam section. In this case, B is the width of the beam, capital D is the total depth of the beam, and small d means that is from top of the beam to the tension zone reinforcement center, that is called effective depth. In this case, this particular beam is divided into two beams. That is, first one is a singly reinforced beam which can resist up to a limiting moment of resistance, and this is section 2 which can resist the balance moment. So finally we will get the doubly reinforced section by adding these two sections. So these are the properties of a doubly reinforced beam section, as we already seen in the previous slide. That is, B is equal to width of the beam, small d is equal to total depth of the beam, that is from top of the beam to the center of the tension reinforcement, and total d is the, that is total depth is the capital D value. And here we will get some new one, that is d prime, that is from top of the beam to the center of the compression reinforcement. Actually this is the neutral axis. So above the neutral axis this is compression zone, and below the neutral axis this particular zone is tension zone. So this doubly reinforced beam section is divided into two beams, that is beam A and beam B. Beam A means resisting balancing moment, that is mu1, that is limiting moment of resistance. So in this case, limiting moment of resistance is calculated as a singly reinforced beam which is having only tension reinforcement, that is AST1, and the resisting balance moment. Balance moment means whatever the difference amount that is more than the limiting value is known as the resisting balance moment. In this case, we are considering it as an imaginary section. The balancing moment will be designed for AST2 and ASC values. So these are the stress block parameters of a doubly reinforced beam. In this case, if we draw the doubly reinforced beam stress block parameters, in this case this is the neutral axis and this is the total tension offered in that particular beam section, and this is the total compression in the compression zone. And if we draw a stress block parameter for a resisting balancing moment, that is a singly reinforced beam section, total tension is equal to 0.87 Fy into, here we are having AST1, that's why 0.87 into Fy into AST1, and total compression C1 is equal to 0.36 FCKB x nu, which we already seen in the singly reinforced beam section. and it will act at a distance of 0.42 x nu from top of the beam, and here we will get 0.446 FCK in the top, and the lever arm is D minus 0.42 x nu. So this is the singly reinforced beam which will resist the balancing moment of Mu1. And if we see the doubly reinforced imaginary section, in this case the tension steel is located the compression steel is located at a distance of D prime from the top of the beam. There we will get C2 is equal to FSC minus FCC into ASC. So FSC means the stresses of steel in the compression zone, and FCC is the stresses in the concrete in the compression zone, and ASC means area of steel in the compression zone. Here T2 is equal to 0.87 Fy into AST2. The distance between the C2 and T2 is equal to D minus D prime, that is called lever arm. Design steps. First of all, we have to find out the limiting moment of resistance for the given cross section. As we already seen in the singly reinforced beam, for different grades of steels we will get the limiting moment of resistance values. For Fe415 grade steel, the Mu limiting value is 0.138 FCK BD square, and for Fe500 it is 0.133 FCK BD square, and for Fe250 it is 0.148 FCK BD square. By substituting the values, we will get the limiting moment of resistance value. After getting the limiting moment of resistance value, we have to compare with the Mu value. If Mu is exceeding the Mu limiting value, the doubly reinforced beam section is required to be designed for the additional moment. In the previous singly reinforced beam section cases, we are getting Mu less than Mu limiting, so which is a under reinforced section. But in this case, Mu is greater than Mu limiting, so we will get a doubly reinforced beam section here. So Mu minus Mu limiting is equal to the balance moment, that is equal to FSC minus FCC into ASC into this particular distance, that is lever arm distance, that is D minus D dash. So here FCC value will be very negligible value. Why? Because FCC means compression stress in concrete at the level of compressive steel. So in the location of steel value, the compressive stress will be very negligible value. That is, FCC is very lesser than FSC values. So in this case, we will neglect this FSC value. So finally, Mu minus Mu limiting is equal to FSC into ASC into D minus D dash. FSC is equal to stress in the compression steel. So the additional area of tension steel AST2 is obtained by considering the equilibrium of forces of compression, that is C2 in the compression steel and force of tension T2 in the additional steel, that is total compression C2 is equal to total tension, that is T2. So by equating these two, FSC ASC minus FCC ASC is equal to 0.87 Fy AST2. So FSC ASC is equal to 0.87 Fy AST2. By using this equation, we will get AST2 value. Then total tension steel is equal to AST is equal to AST1 plus AST2. Depth of neutral axis. For finding out the depth of neutral axis, we have to equate total compression is equal to total tension. That is C1 plus C2 is equal to T1 plus T2. That is 0.36 FCK Bx nu is the C1 value. FSC into ASC plus FCC into ASC is the C2 value. By equating this equation to total tension, that is 0.87 Fy AST, we will get x nu is equal to 0.87 Fy AST minus FSC minus FCC into ASC by 0.36 FCKB. In this case, we will neglect that FCC into ASC value is very minimum value. When compared to FSC into ASC, we will delete that one, and further we will get x nu is equal to 0.87 Fy AST minus FSC into ASC by 0.36 FCKB. By using this equation, we can calculate the depth of the neutral axis x nu value. This is the doubly reinforced beam which is having a B width and small d effective depth, and D prime is the distance between the top of the beam to the center of the compression reinforcement, and in the top of the section we will get the maximum strain of 0.0035, and here it is the proof stress, that is 0.002, and in the bottom it is 0.87 Fy by S plus 0.002. So this is the FSC value, that is design stress in compression reinforcement, corresponding to a strain of 0.0035 into XU max minus D prime by XU max. By substituting the XU max values and D prime values, we will get the strain value of epsilon SC value. After getting the epsilon SC value, we have to find out the stress value by using the stress strain curve graph. So this is the stress strain curve graph of a cold work with deformed bar. For example, if we got the epsilon value of 0.002 by using this straight line curve, and after touching it to Fy by 1.15 curve, just calculate the stress value, that is 0.85 Fy. So by substituting the Fy value in this 0.85 Fy value, we will get the stress value for that corresponding strain. After calculating the FSC value, we have to substitute the FSC value in mu minus mu limiting equation. Mu minus mu limiting is equal to FSC into ASC into D minus G dash. By solving the equation, we will get area of steel in the compression zone, that is ASC value. After getting the ASC value, substitute the ASC value in AST2 equation, that is AST2 is equal to ASC into FSC divided by 0.87 Fy. We will get AST2 value. Then total AST is equal to AST1 plus AST2. So finally we will get the total compression steel, that is ASC and AST values. By using these equations, we can design the doubly reinforced beam section in the further videos. So please kindly subscribe Civilly Learn for more videos.